Alaikum. Let's start lecture number 27. That is a tutorial basically, and we will solve two problems. One from the section 5.1, that is shear force and bending moment diagram using the static equilibrium condition. That is sum of forces is equal to 0, sum of the bending moment is equal to 0. Now, for that is problem 5.23. And we will solve another problem from the relation among load, shear and bending moment. That will be problem 5.56. Okay, let's start with problem 5.3. 5.23, let's see. Draw shear force and bending moment diagram for the beam and loading shown and determine the maximum normal stress due to bending moment. So for this beam A to AH, we have to find the maximum bending moment, and using that maximum bending moment, we will find maximum normal stress. Okay, now if you look at this beam, so we have support at A, roller support at D and H, and there's a hinge as well. Now this hinge, the moment will be equal to 0 because it on that hinge it can free to rotate, so that's why the moment will be equal to 0. So we have another information, so moment is equal to 0 over here. Now if you look at the loading, so this beam we can divide into two segments, AE and EH. Now this AE, if we roughly draw, if we look at that, this will deform something like this, and then it will try to move upward this point E, and these forces will push it downward. So if I look on E, so the force at E for segment EH will be upward direction, and force on section AE will be downward direction at E, because at E this force and these forces E over here and E on segment AE both will be equal, and we can treat them as a separate beam. Okay, so if you draw free body diagram, so E, H, and we have forces over there. So let's talk about segment EH. Sum of moment at E is equal to 0. So H we can find, that is 213.33 Newton. And if you take sum of forces in Y direction is equal to 0, or vertical direction is equal to 0, we can find the value of E, that is 126.67 Newton. And that will be same E over here. Now, if we take moment about A is equal to 0, so we can find the value of T, that is 468.89 Newton, and sum of forces in vertical direction is equal to 0. So A will be equal to 257.78. By drawing free body diagram, considering as a rigid beam, by applying static equilibrium condition, we can find the reaction forces and also force at pin at E. And now remember, on that spin or hinge, the moment will be 0. Okay, now we already calculated the forces, reaction forces, external forces. Now we have to draw shear force and bending moment diagram by considering the internal forces. Okay, now first we will consider segment EH. For segment EH, we already calculated the force at E and H, right? And we will take a section at different location, and using that section we will find the shear force, internal shear force and internal bending moment. Okay, now let's take first section between E and H, E and F, just before F. So let's take a section over here, and now we will find the shear force and bending moment, and that will be for segment E and F. Okay, now if we draw free body diagram for this segment, So we have force E acting upward direction. Now we have shear force. Let me write V1 and the moment M1. And this distance, since we are going from left to right, so this distance we will take as x. Okay, now we consider this beam as separately EF because of this pin joint or hinge, and the shear force will be constant between E and F because there is no distributed load. So if there's a point load, so the shear force will be constant. So if I want to write V1 minus E, and that will be equal to 0. And this leads us to V1 is equal to positive E, and that is 126.67 Newton. Now, and that will be constant between E and F, this value of V1. And now moment, now if we want to write moment expression, M1, let me write M1 minus EX is equal to 0, and M1 will be equal to E times X. And if you look at this expression, that is a linear expression, and that is valid for section EF. Now if you put X is equal to 0.2, so according to the dimension, so as mentioned here, 7 at 200 millimeter means the distance between each segment A, B, B, C, C, D, and E, F, and F, G, H, G, H is 0.2 millimeter, and total length is 1400 millimeter. So if you put X is equal to 0, that is MA, moment at A, and it will be equal to 0. And if I put X is equal to 0.2 meter, so that is moment about C. So let me write M1, and that will be equal to MC. And if you put X is equal to 0.2 over here, we know the value of E. So the moment will be 25.33 Newton meter. Okay. Now let's consider this section for section FG. Now we will considering shear force and bending moment diagram for the section F. Sorry, not E. So that will be FG. So let me FG. So let me draw free body diagram for that segment. So we have E. We have one force of 40 Newton, and this distance will be how much? 0.2 meter. And we have shear force acting. Let me take V2 and M2. And obviously this distance will be X. So if you want to write the expression, so V2 plus 40 minus E is equal to 0. Now if you put the value of E and 40 Newton, we already put it, so V2 will be nothing but 86.67 Newton. Okay. Now, okay, let me erase this line. And let me draw again. Let me try talking. Okay, now better. Now for the moment, M2. Okay, now 40 Newton plus 40 into X minus 0.2. minus E into x is equal to 0. So this is the equation for the moment. And now if I put x is equal to 0.4, so this is point H. So moment, sorry, not H, G. So if I'm interested, what is if I put x is equal to 0.4, so that m2 will be equal to mg, and if I put in equation, so that m will be equal to 42.67 Newton meter. Okay, and if I put x is equal to 0.2, so this expression will become 0 and it will come back to the value of m1, that is at point C. Now let's take a section just after G, and now this time we are only this segment. Why? Because we have deal with the only two forces and it's easy to calculate. So let me draw free body diagram for that segment. Now since we are taking section from right to left, so the shear force will be taking upward as a positive. So let me write V3, and we have, let me write M. Okay, and we have a force H acting upward direction. So V3 plus H is equal to 0, and V3 is equal to minus H, and I know the value that will become 213.3 Newton. Okay, now this distance will be what? That will be equal to L minus X, because we're taking from section from right to left. So for this segment EH, the total length is 0.6 meter. So that will become 0.6 minus X. Okay. Now if I want to write the expression for moment, so let me write M, right? And minus H into 0.6 minus X is equal to 0. Now in this case the X will be 0.4, because if we talk about location at G, so this distance is 0.4. So if we put X is equal to 0.4, so that will become M minus H into 0.2 is equal to 0. And if I put the value of H, so we have same value of M as we calculated for M2 or Mg, that is 42.67 Newton meter. And if you put X is equal to 0.6, that is point H, so moment at H will be equal to 0. And it's a common sense as well, since it's a pin joint over there, so the moment is, and it's an end pin joint, so the moment should be equal to 0 at that location. Okay, so these are the shear force and bending moment at different segment. So this is for FG, and this working is for GH. Okay, now so we have the shear force and bending moment for EH segment. So we will now consider segment AE. Okay, now for segment AE, we already know the forces A, D, and E. So, and we will take a segment. So first we take a section just before B, and that is valid for the AB. The working is valid for AB. And if we draw free body diagram for AB, so we have A acting upward direction. So let me write this shear force V4, and we have a moment. Let me write M4. Now A V4 minus A is equal to 0, and V4 will be equal to 257.78 Newton, and that will be constant between A and B. Now, for the moment, again, this distance, since we are taking section from left to right, so we take an x. So M4 minus AX is equal to 0, and M4 will be simply is equal to AX. Now x is equal to 0, that is point A, so moment at A will be 0, because at A, x will be equal to 0. Now M4, now if we put x is equal to 0.2, that is at B, this location, so when x is equal to 0.2 meter, so the value of M4 will be equal to 51.56 Newton meter, and that will be equal to MB. Okay, now let's take a section over here just before C, and let's draw a free body diagram for that. So we have, let me erase this one and draw again. Okay, let me draw again. So we have A, we have 300 Newton acting downward at B, and we take a section just before C. So we have a shear force acting downward. So let me write V5, and let's take moment as M5. And this is valid for segment BC. Okay, now let's write the expression for shear force. So V5 plus 300 minus A is equal to 0, and V5 we put the value of A in this expression, so it will be simply minus 42.33 Newton. Now for the moment, let me write M5. Okay, now this distance, since we're taking section from left to right, x, and we know this distance is 0.2. So we can write M plus 300 into x minus 0.2 plus, sorry, not plus, minus a into x is equal to 0. Now if I put x is equal to 0.2 meter, so that is simply, we come at point B, and that moment will be equal to M4. So that will be equal to moment at B. But if we want to calculate at C, so we have to put x is equal to 0.4 meter in this expression. So M5, so that will become MC, and if we put the value of 0.4 meter, so that value of moment will become 43.11 Newton meter. Okay, now again there's a point load between at B, C, and the variation of shear force will be linear, and bending moment, sorry, shear force will be constant and bending moment will be linear. So at B it will be 51.56, and at C it will become 43.11, and the variation will be linear. Now let's calculate for the segment CD and DE. Now for segment CD, so let's take a section just over here, and let's draw a free body diagram, and that is valid for segment CD. So if I draw a free body diagram for that segment, so let me take the shear force for segment CD. So that shear force acting downward. So let's take V6 and moment M6. And we have A, we have one force acting B, that is 300 Newton, and we have another force of 300 Newton, and the distance between these two forces is 0.2 meter, and from A to this force at D is 0.2 meter. And we take this as a X. So always remember that take in terms of X. So we have to write an expression for that, and it will be useful for chapter 9 as well. So V6 plus 300 plus 300 and minus A, and this will be equal to 0. And V6 will simply equal to minus 342.22 Newton. Okay. Now for the moment, so let me write M6, the expression will be plus, now force at C, 300. Now distance from, again moment we are taking from this point, so this distance will be X minus 0.2, 0.4 plus 300 and X minus 0.2, and this force at 300, this force of 300 is at B, minus AX is equal to 0. Okay, now if I put X is equal to 0.4, so I will come at point C. Okay, so this expression is valid for only section CD. Now at X is equal to 0.6 meter, that is at point D, so M6 will become MD, moment at D, and if you put the value of 0.6, so that is minus 25.33 Newton meter. Now, and this, now let's take a last segment. Now for the last segment, so let me take section just after D and eliminate or remove this section, and I'm only considering DE. So this will be valid for section DE. So if I draw free body diagram, so we have E, E will be acting downward, not upward. So let me erase this one. Okay. And shear force will be acting upward, we will take positive. So let me write this is V7 and moment. Okay, so let me write M7. So sum of, and this distance will be nothing but L minus X, or this segment the length is 0.8 minus X, since we are taking section from right to left. So E plus V7 is equal to 0, and V7 will nothing but negative value, E plus V7, not minus E, because upward direction is a positive, so it will, V7 will be positive, that is 126.67. And it's a hinge joint, so moment at E will be equal to 0, and a moment at D will be equal to M6, and that will be equal to minus 25.33 Newton meter. And you can also calculate from this expression as well. Okay. Now we know the moment that and shear force at all the section, and let's draw shear force and bending moment diagram for this problem. Okay, now we have already noted uh, for segment EH, V1 is 126.67. It's a constant between this segment. For segment EH, then V2 we calculated and it's constant between FG, and we also calculated V3 and it's constant between segment GH. Similarly, we calculated V4, that is shear force, constant shear force. It will be constant between AB. From BC, V5 minus 42.33, and for CD it will be minus 342.22, and from DE it will be 126.67. So we know the value of shear force between the segment A, B, C, D, E, F, G, and H, and let's draw shear force diagram for this. Okay, so uh, from A to B, so shear force is 257 Newton meter. So from A to B, the shear force is 257 Newton meter. So let me write 258. From C to D, it's negative 42.33. From C to D, let me write 42. And from C to D, it is minus 342. So 342 negative. And from D to E, it's positive 126 as well. Let me write 127, and from E to F it's again constant 127, straight line, and then from F to G this is become 87.67, so let me write 87, and from G to H it's negative 230. So basically this is my shear force diagram. So when I draw it, it will be shear force diagram like this. So it's a constant between AB, BC, CD, EF, FG, and GH because there is no distributed load acting on the beam. Okay. Now let's draw a bending moment diagram. So we know the moment at different point, and we know that since the shear force is constant between the segment, so the bending moment will be varying linearly, and we already uh, put the value. So from at A it will be 0, from A to B, so that will change linear. So let me write the value of bending moment. So at B it will be 51.56. So from A to B it will vary linear. From B to C it will change and it will become 41.3. And at C it will become 43.11, sorry. From C to D it again changed linear, but it will become at D it will become minus 25. So if I want to draw, so from C to D it will become, and it will be a straight line, and at D it will become minus 25.3, and it will be 0 at E, and it will at F it will become again 25. So it should be 0 at E, and at F it will be 0 at again E, it should be 0, and at F it will become 25.3. Now from at F to H it will again increase, and this increase, and it will be 42.7, and H it will be 0, so it will be 0 at H. Now the maximum bending moment is 51.56. Now we have to find what is the maximum normal stress for this beam. So we know the moment. So the maximum moment, max, if I want to write max, so that is 51.56 Newton meter. Now we have a rectangular cross section. So section modulus for rectangular is 1 by 6 bh square, putting the value in terms of meter, 1 by 6.2 b, h is 0.3. So if we calculate, that become 3 10 to the power minus 6, and sorry, this will become meter square, not millimeter square. Okay, so this will become meter square, meter cube, sorry. So maximum normal stress, the flexural stress formulas, m over s in terms of section modulus. So we put the value of maximum bending moment 51.56 Newton meter divided by 3 into 10 to the power minus 6 meter, and if we calculate, so this will become 17.9 10 to the power 6 Newton meter, or we can write 17.9 megapascal. So in order to find maximum normal stress, we have to find where is the maximum bending moment, and we can do with using shear force and bending moment diagram. So now let's see another problem, but this time we will draw shear force and bending moment diagram using the graphical method. Okay, let's see problem 5.56, and we have to draw shear force and bending moment diagram using graphical method. So we have a overhanging beam, beam AB. We have a point load of 9 kilonewton acting at A free end. At C we have a support, at B we have a support, and we have a distributed load from C to B, uniformly distributed load of 12 kilonewton per meter. Okay, so first what we'll do, we will draw a rigid body diagram for that beam to find the reaction at C and B. So this is a free body diagram, and this distributed load will be, we can change into concentrated load, and that will be equal to 12 multiplied by 3, or so that, and it will be acting at 3 by 1.5 from the 1.5 meter from the B, or 1.5 from the C, or you can say at midpoint of B and C. Okay, now if you take moment about B, so you can calculate the value of C, that will become 29.7 kilonewton. And if you calculate moment about C, so you will get the value of B of 15.3 kilonewton. Now the cross section of the beam is given, it's a W200 by 19.3. So this beam, so cross section is given, so we will use appendix C of a textbook to find the sectional property of this beam. Okay, now let's draw shear force and shear force for this problem. Okay, let's draw shear force and using the relationship. And so for segment AC, it will be very straightforward. So there is no distributed load, so shear force will be constant between A and C, and that will be for AC. So let me write for AC. It will be simply what V, uh, and the shear force will also acting on the same direction as V, so it will be minus 9 kilo Newton. Now, just after C, just after C, so let me write, this is C plus, So V will be equal to minus 9 kilonewton plus 29.7 kilonewton, because there is a shear force acting, external shear force acting at C here. So we are calculating just after C at this location. So obviously the effect of this shear force will also include. So V will be, for after C, it will be 20.7 kilonewton. Means from A to C, it will be remain minus 9 kilonewton. So from A to C, the shear force will be minus 9 kilonewton. Let me draw again. From A to C, it will be minus 9 kilonewton. And from C, it will move from minus 9 to 20.7 kilonewton. So this will be 20.7 kilonewton, and this value is minus 9 kilonewton. Okay, now what will be the shear force at B? So we can write the expression. So that expression will be simply VB minus VC, and that will be equal to area under this distributed load. So, and minus sign. If you remember the relationship between shear force and bending moment. Load and shear force. So VB is nothing but VC minus area under this load curve. So that is 12 into 3. And we already calculated the value of VC. So VB is nothing but 20.7 minus 36. And VB is minus 15.3 kilonewton. Means from 20 kilonewton, so it will become minus 15.3 kilonewton. And since we have a uniformly distributed load, so variation of shear force will be linear. So this variation will be linear. Now, shear force is 0 at this location. So, and if you remember that the relationship between shear force and bending moment, so slope of the maximum bending moment is occur where the slope is 0, or in other words, where the shear force is 0, means when dm by dx is equal to 0, so means the shear, and this is equal to shear force. So we have to find the location where we have maximum value of shear force. Now, but we don't know the location of this point. Let's take this as E, and if we can calculate the value of E, so we can find the location of where we have maximum bending moment. And value of maximum bending moment we will see. And this distance will be 3 minus E, because this segment, this is from C to B. So this whole segment is equal to 3 millimeter, sorry, not millimeter, millimeter. So now we have two triangles, so two similar triangles, so we can take the ratio of triangle. So we can write E divided by 20.7, and that will be equal to 3 minus E divided by 15.3. So by solving it, so value of E is equal to 1.725 meter. So from C, the shear force will be 0 at 1.725 meter on this location. And over here we will have maximum bending moment. Now for maximum bending moment, we have to find area under this curve. Okay, so area under this shear force curve will be minus 9 multiplied by 0.9. So that will become minus 81. So let me write A1, A2, and A3. So A1 will be simply 8.1 kilonewton meter and with a minus sign. And that will be moment at point C. Now A2 is equal to area under this curve. So area under this curve is, this is a right angle, this is a triangle, right angle triangle, half base into height. So let me write over here. Now let me change the pen. So I can write A2 1 by 2 height, base into height. So base is 1.75, 1.725 multiplied by 20.7, and it's a positive value because, so let me write this is A2, and if I calculate, so that will become 17.8537, 17.853 kilonewton meter. And this value of A2, we can calculate moment at E, and obviously the moment at B should be equal to 0. So let's calculate area for this one and we will see what will be the moment at B. So A3 is nothing but 1 by 2, base is 3 minus E, so value of 3 minus E will be minus 1.2 1.275, 3 minus 1.725, and this height is 15.3, and A3 is how much? Minus 9.75 kilonewton meter. Okay, now let's we know the area, and now we can calculate what will be the bending moment using the relation between shear force and bending moment. Okay, let's calculate shear force and bending moment diagram. Let's draw bending moment diagram using the shear force area under the shear force curve that we already calculated in previous slide. A to C, area under the curve A to C was minus 8.1 kilonewton meter. From C to E, E is a location where we have zero shear force. E is the location, let me write over here, E at which we have V is equal to 0 and the moment will be max. And the slope of the curve will be 0. And A3, that is from C to B, the area under the curve, shear force curve, the value is minus 9.575 kilonewton meter. Now we will calculate the moment at C, E, and B. So area, now let's take MA1. So we can write MC minus MA is equal to area under the curve A1. MA is 0, so MC is nothing but area A1, and their value is minus 8.1 kilonewton meter. And if we know the shear force was constant between A to C, so the bending moment will be linear between A and C, and at C it will be 8.1 kilonewton meter. So let me clearly write this. So that is 8.1 kilonewton meter. From A to C minus 8.1 kilonewton meter. So it will be from A to C. So this value at C will be approximately minus 8.1. And let's take this scale into kilonewton meter. Okay, now we have to calculate what is the E at E. So ME E minus MC will be area under the shear force curve that we already calculated, that is A2. So if we put the value, so ME will be simply A2 minus MC. We know the value of MC, that is 8.1. A2 is we calculated, that is 17.85, and this will become positive 9.753 kilonewton meter. So means from C to E, it will be on this point. Let's take this point, and this variation, now this variation will be quadratic. It will not be linear. It will follow some curve, and it will be a follow some curve. It will not be a straight line. Now at B, so we can calculate MB minus ME, and that will be area A3. Now MB will be simply equal to A3 minus ME. Now if you remember, we calculated M3 was 9.753, and A3 we calculated that was minus 9.75. So if we put the value in this equation, sorry, this is plus, so MB will be approximately equal to 0, and if it's a pin joint at the end of the beam, so obviously the moment should be equal to 0, and this is verifying this. So this will be again from here to here, it will be a curve, not a straight line, and the maximum bending moment value is 9.753 kilonewton meter. So this is the maximum bending moment, and it will be at location E. Now we have to find the maximum normal stress and maximum bending moment. M, we can write that will be acting 9.753 kilonewton meter, and it will be acting at E. Now we have a beam W200 by 19.3. If you go at Annex C of your book, of a textbook, you will find under the beam W200 by 19.3, the section modulus for this cross section is 164 10 to the power minus 6 meter cube. So maximum stress will be M over S, and we know the value of M, 9.753 10 to the power 3 divided by 164 10 to the power minus 6. Now maximum bending moment, so maximum sigma max is, when we calculate, so that is 59.5 10 to the power 6 Newton per meter square, or we can write 59.5 megapascal. Now, this method is known as graphical method, um, and we can draw shear force and bending moment diagram using the relationship between load, shear force, and bending moment. Now, this graphical method, when you have a load like this, these type of loading that is shown in this example, it will be easy to calculate, but for the complex load, it will become difficult. So, my opinion that you should learn both the method, but for me, the previous method where the previous example we did using the sum of forces is equal to 0, sum of moment is equal to 0, that equilibrium condition method, the finding the shear force and bending moment is easier. Now, for the value of maximum bend, and you can take the hybrid approach as well, but we have to write the moment equation, okay, in terms of x. We must learn that because for the deflection of the beam, we need that equation. So thank you very much, and we will discuss further in interactive session, and I will answer your queries or any question on that interactive session. Thank you very much.